Ever wonder what's really going on inside our massive electric grids to control all that power? Or how an industrial motor knows exactly how fast to spin? Well, behind the scenes, deep in the heart of all that powerful hardware, there's a special family of components called thyristors. And honestly, they're the unsung heroes, the real gatekeepers of electricity. Okay, so here's the game plan for our journey today. First, we're going to lay down the family rules, how all thyristors turn on and off. Then we get to meet three very cool specialists with really unique jobs: the super precise SUS, the all-in-one RCT, and the seriously powerful SITH. And to wrap it all up, we'll take a peek into the future with what's next: silicon carbide. Let's get into it. So what in the world is a thyristor? The easiest way to think about it is like a high-power electronic switch. It's got no moving parts, but it can control absolutely massive amounts of electrical current, switching it on and off with incredible precision. And when I say massive, I really mean it. The gear you're looking at here, those are thyristor power controllers. These things are the workhorses in everything from motor speed controls and huge power converters, all the way up to the high voltage DC or HVDC transmission lines that literally move electricity across entire continents. So to really get a handle on the different family members we're about to meet, we first have to understand the two fundamental rules that they all live by: turning on and, of course, turning off. The on switch for a thyristor has a special name. It's called triggering. It's just the process of taking the device from its blocking state, where basically no current is flowing, to its conducting state, where the floodgates open and current flows freely. Now, as you can see, there are actually a few different ways to flip this switch. You could do it by hitting it with a high voltage, using temperature, or even using light for some special optical versions. But for precise control, the one that's used almost all the time is gate triggering. This is where a tiny little electrical pulse to a pin called the gate acts like a key, unlocking the main flow of current. Okay, but turning a thyristor off, that's where things get really interesting. This process is called commutation, and here's the most important rule you need to remember. Unlike a normal switch, you can't just send another signal to turn it off. The only way to shut it down is to get the main current flowing through it to drop below a critical point, which we call the holding current. And how you manage to do that really depends on the circuit. On the left here, if you're in an AC circuit, the job is basically done for you. The current naturally drops to zero and then reverses direction every single cycle, which automatically turns the thyristor off. We call that natural or line commutation. But over on the right, what about a DC circuit? The current is just a constant flow, so you have to get clever and use an external circuit to momentarily interrupt that flow and force the current down to zero. That's what we call forced commutation. All right, now that we know the family rules, let's meet our first specialist. This is the silicon unilateral switch, or SUS for short. And this little guy is designed to solve a very specific problem. How do you trigger a much, much bigger thyristor at exactly the right moment? The SUS is, for all intents and purposes, a miniature thyristor. Its entire job is just to act as a highly predictable trigger. It's a low-power device, so it's not doing the heavy lifting itself. No, instead, it provides that clean, sharp, perfectly timed pulse needed to fire up its bigger, more powerful siblings. And what makes the SUS so special is right here in this VI curve. Just watch what happens. As the voltage across it goes up, almost no current flows. It just waits and waits. But then, the second the voltage hits a very precise, predefined point, the breakover voltage, bam, it instantly snaps on and lets the current rush through. This predictable snap action is what makes it the perfect, most reliable trigger. Okay, so our first specialist was all about starting things precisely. Our next family member, the reverse conducting thyristor, or RCT, is all about efficiency and just plain smart integration. This slide just illustrates the whole idea perfectly. Over on the left, you see the circuit symbol. It's a thyristor with a diode connected backwards right across it. Then, on the right, you see the actual component. The RCT takes those two separate parts and cleverly builds them into one single integrated package. So you might be asking, what problem does this actually solve? Well, in a lot of circuits, especially ones driving motors, you need an extra part called a freewheeling diode to safely handle reverse current. The RCT simply builds that diode right in. Now, it can't block reverse voltage anymore, but it doesn't need to. That built-in diode takes care of it automatically. And the benefits of doing this are huge. Right away, your circuit is simpler with fewer parts to worry about. But the real genius here is thermal. See, since the thyristor conducts the forward current and the diode handles the reverse current, they are never both on at the same time. This means they don't produce heat simultaneously, which makes it way, way easier to cool one compact package instead of two separate hot components. And now, let's meet the powerhouse of our specialized group, the static induction thyristor, or SIT. This is the family member that was built from the ground up for high-power, high-speed applications. Here we have the SITH, both its symbol and its really robust physical package. You can tell it's made to handle serious power. What really sets it apart is that it combines brute strength with incredible speed, way beyond what a standard thyristor can do. And, get this, it can be turned both on and off right from its gate. So what makes it such a powerhouse? It's this unique mix of traits. It can handle massive currents, but it does it with an extremely low voltage drop, which means very little energy gets wasted as heat. And its real superpower, it can turn off incredibly fast. You know, these features really make it a beast. It's got a faster switching speed than similar devices like the gate turn-off Thyristor or GTO. It's more efficient because of that low voltage drop, and it's highly resistant to electrical noise. This specific skill set makes it the perfect choice for the most demanding jobs, like high-frequency power conversion. So we've met the specialists, but the whole Thyristor family tree is always evolving. And the future of power electronics? Well, it's being built on a completely new foundation. And that foundation is silicon carbide, or just SiC. This material isn't just a small improvement, it's a revolutionary leap forward for all kinds of power devices, and it's carrying on the Thyristor's legacy. So why should you care about this? Well, SiAC devices are just dramatically more efficient, which means less energy is wasted as heat. This allows them to be much smaller and lighter, and often they don't even need bulky cooling systems. This is the technology that's making the next generation of electric vehicles, solar inverters, and modern power supplies smaller, lighter, and more powerful than we ever thought possible. So when you look at the big picture, from the basic principles of triggering and commutation all the way to the specialized roles of the SUS, RCT, and SIT, you can see that the core ideas live on. But as technology marches forward, the physical form evolves, pushing the boundaries of what's possible in power control. And that leaves us with one final thought. We've seen how this family has evolved, with each member finding its own special purpose. But as these incredibly efficient new SiC devices start to take over, which of the specialists we met today, the SUS, the RCT, or the SIT, do you think will be the first one to retire and become a legend of electronics history?
Thanks for watching. Please visit the channel for such more content, and don't forget to subscribe the channel and like if it is helpful to your knowledge, and comment if something is wrong.